Today we are going to demonstrate the photoelectric effect experiment. In this experiment, we will show how to take the measurements of the photocurrent. So let's start with the theory. So using the virtual lab, we will simulate the photoelectric effect experiment and go for the photocurrent measurement, and we'll find the threshold voltage for which the photoelectric effect will stop. So threshold voltage in this case, it will be a reverse voltage, so we will discuss later. So let's go through the theory first. So in the theory part, you can see the aim, theory, the important observation in photoelectric effect, and the calculations along with the graphs. Graph connecting photocurrent and the applied reverse potential for constant frequency and different intensity are also given. So in the theory part, we can find what is actually the photoelectric effect, and we know that when there is a metallic surface and a photon, that means the light of a particular wavelength, is falling on the top of this metal, there will be generation of electron, provided that the frequency is high enough so that it could be achieve that level of kinetic energy to come out of this surface. This minimum frequency for which there will be emission of electron, that means the photoelectric effect will be observed, is termed as the cutoff frequency, and it is related to the work function of the material. The work function of the material determines the at which frequency the photoelectron will be ejected. Now, as we know, this photoelectric effect is an instantaneous process. Whether the process will happen or not, it depends only on the cutoff frequency. If the the incident frequency is higher than the cutoff frequency, then only the photoelectric effect will happen. The photoelectric effect, the incident of photoelectric effect, doesn't depend on the intensity of light. Only the photocurrent, that means the number of photoelectrons emitted, that is only proportional to the intensity of incident light. If the intensity is high enough, even if the intensity is high enough, but the irradiance, that means the incident light, doesn't have the frequency equal or larger than that of cutoff frequency, there will be no emission of electron. When that condition will match, that means the incident frequency will be higher than the cutoff frequency, then only then the photoelectron will eject. What will be the kinetic energy? That energy will depend on the energy of the incident photon, that means the frequency. The energy of the photon is related to its frequency by this relation E equals to h nu. Now coming to this W is the work function of the metal, and it is given as h into nu 0. This nu 0 is called the cutoff frequency, and h is the Planck's constant. When there is incident light of frequency nu, the total energy will be h into nu, and this h nu will be distributed in two parts. That means it will be, one part will be used to overcome the work function of the metal. The second part will be used to achieve a kinetic energy that is called Ke max for the electron. Now after some mathematical calculation, we can see this Ke max equals to h times nu minus nu 0. To find the h value, we have to find out this Ke max, which is eventually equals to the stopping potential into electronic charge. If we could be able to find out the stopping potential for a particular frequency, for a particular metal, then also only we will get this Ke max. By putting this Ke max value here and knowing the work function and the incident frequency, from the work function correspondingly we could find out the nu 0, that means at which that photoelectric effect is going to be happen. So in this case we can find out the changing the nu value, and we will observe at what nu value the photoelectric effect is being observed. And for a particular nu value which is higher than this nu 0, we have to find out this EV0, that means the stopping potential. Stopping potential means this is we can easily find this the maximum kinetic energy, that is K max. Putting it here, we can easily find out the value of H. For different materials, we will have a different Ke max corresponding to the frequency. The cesium has different cutoff frequency, and also the calcium. Hence, we will have a different Ke max. Now coming to the simulation part, what we have to do is, first of all, this simulator is coming with actually pre-implemented circuit, so we no need to implement any type of circuit here, but we have to do something that is called the switch on the light option is here. You can see the materials are given, so copper, sodium, this is zinc, platinum, and one material is unknown. So let's go with this switch on the light. After switch on the light, we can see these 1 2 3 4 panels are basically turned on. So in this case we can change the area of the plate. The plate is actually here where the light is falling. Now this area of the plate means there is a barrier actually. If we increase the area of the plate, that means the more number of more number of photons will fall on the surface, because the surface actually which is actually exposed to the light will be increased. Now coming to the intensity of the light, so intensity means the number of photons actually. So it actually the more the intensity of light, more the number of photon will fall on the surface, and this is the applied voltage. So in this case you can see this is the negative voltage, so we are actually using the reverse voltage. So now coming to the wavelength of the light, so you can see this is the light. Now as we are here, that is around 100 nanometer, this actually range is for the ultraviolet. If we choose it and we just increase the value, just you're requested to look at the color of this light. This is actually, this will be increased, this wavelength is increasing, that means the frequency is decreasing. There is a shift from the violet to red through blue, green, yellow, orange, red, 750 infrared. So now coming to this wavelength part, what we have to do is we have to first of all choose a particular material. For example, the default is copper, let it be in copper. Now I'm just selecting the area of the plate as 0.4 centimeter square, the intensity of light as 15 watt per meter square, and keeping this wavelength of the light at 100 nanometer. So we don't need to change 1, 2, 3 right now. We will change only this frequency value, and we will change this frequency value 5 times. The whole thing will be called as set 1. I'm repeating it again. I'm just keeping this copper constant, that means the material constant, the area constant, the intensity of light constant. So this is my set 1 parameters. Under the set 1 parameters, we will only change the wavelength 5 times. For 5 different wavelengths, we will measure this applied voltage, that means reverse voltage from here, and the current. So let's start. So this is my set 1. Now I'm keeping this wavelength at 100 nanometer. So I'm just increasing the negative voltage value from 0 to a value until the current becomes 0. So this is the value for which we got a 0 current, and this voltage is called the threshold voltage. So what we have to do, we have to note in the workbook, that means the table book. So there will be a voltage part, and the another part there will be current, reverse current. So sorry, this is the current part. So in the one table there will be a voltage, another part there will be current. So we will start from 0 and slowly we will increase the negative potential, and we will reach up to this point where the current value is 0. So this is for one wavelength, that is 100 nanometer. We can get at least 15 to 20 readings for a reasonable interval. Suppose this is 7.8, I think. Yeah, 7.8 we are getting this. So we can change the value for the interval of 0.5. For 0.5 interval we can change the value so that we can get a very reasonable number of data. Now coming to the next value, we will increase this wavelength. Suppose for 120 nanometer, keeping this constant, we will not touch this. Keeping it at 0, we will start taking the reading. We will increase the negative potential, for which we will get a 0 current, that is called the stopping potential at that wavelength. It's around minus 5.70 volt. So we'll take another value, another table data, keeping this wavelength constant. So there will be a V versus I. So we will start from 0, we will end up to here. To get the 0 current, we will take a handsome amount of data for a reasonable interval. That interval you have to choose it. Now I'm taking another data, that is for say 150 nanometer. We'll start from 0. Again we are repeating the experiment for a different wavelength. So in this way we will find an IV curve for a set 1 for 5 different. I have shown you 3 for the how to take the data for 3 different wavelengths. Now what you have to do, you have to take at least 5 for the 5 different wavelengths. You have to take the VI value and you have to plot it in one graph. So for 5 different wavelengths we will get 5 set of data for this VI. So we have to draw the 5 set of VI curve in one single graph. Now coming to the set 2, we will repeat the same thing, but we have to change either this one or this one. So let's change this one, the intensity of the light. Let's see what will happen. We'll start from 100 itself, coming to 0. So as we can see, the threshold at when that was 10 watt per meter square, the threshold that is 15 watt per meter square, the threshold was around 7.8. let's see, in this case this is actually 7.8. so actually there is no effect of intensity on the threshold voltage. So this is the observation. Now this is the for the set 2 we have taken for one set of data for the one wavelength. Now I am taking the second wavelength, that is around 120 nanometer. Keep it at 120 nanometer. I'm just keeping it 0. Starting from 0, I will again increase the negative potential. Let's come to that potential where I will get the 0 current. I have to keep on increasing and I have to note the data for the V versus I. So in this case this is minus 5.0 volt. So usually you have to change this frequency. Suppose this is for an example, this is 150 nanometer again. Okay, let's take 160. Yeah, so I will start from 0. I will take this value 0, for example 0 volt. So now I am telling how to take the values V versus I. So keep at one column for V, one column for I. So it will be 0. So for 0 volt, the I is, suppose it is given as 3.60, so it is in microampere. So I am just increasing the value. So let me first check where we could find the threshold is around 3.10. so let's take the value for 0.4. so I'm keeping it at 0.4. so this is 0.40. so this is 20.60. so 0.4.80, it's 22.60. say for 1.2 it's actually 18.60, and likewise we can take the further values by this much of increment. Sometimes you could find that when we are increasing it for the 0.4 volt interval, that couldn't be the integral multiple of this 0.4, that value, that 3.1. so what we will do, that whenever we will reach closer to 3.1 we will take more value to have a fine data, fine curve. So all these things were set to. Now for the material is concerned, this is copper. Now you can choose another material, say sodium. You can keep the area of the plate constant. Now you can repeat the experiment for the sodium itself. So after the experiment is over, you are allowed to do some calculations. So in the theory part, the calculations are given. So in the procedure, you can see what to do. So in the theory, you have to go through this theory. Suppose this is metal, the work function is given as, for the platinum is 6.4 electron volt, for silver it is 4.7, and likewise sodium, potassium and cesium are also given. Now your work will be to calculate the Planck constant, to draw the graph between photocurrent and applied reverse voltage for 5 different frequencies for set 1 and 5 different frequencies for set 2. So all of this for today now. If there be any further information, we will let you know. Thank you.